Well, it's my pleasure to welcome everyone to this evening's Yandex ML Open Talk, which at this point, this is a session in a very long-standing series, I feel like. But today we're hosting a special guest, Menua Bedrosian, who is a machine learning researcher at YerevaNN. More specifically, he specializes in research at the intersection of biology and large language models. Even more specifically, framing and representing these biological problems in a way that makes them tractable to deep learning. Actually, last week he was in Singapore presenting such work, and now, this week, fresh back from the conference, we're delighted to host him here and have him talk about the latest and greatest ideas, methods, and trends in machine learning research from around the world. So everyone, please join me in providing a very warm welcome to our speaker, Menua Bedrosian.
Thank you, Philip, for the boards. Hello, everyone. As you already know, my name is Menua. And today I'll be presenting you some of the trends from ICLR that happened a week ago in Singapore. And I guess we can start the slides. First of all, who calls it ICLR and who calls it ICLR? Anyone calls it ICLR here? It turns out people have two pronunciations for this conference. Some people call it ICLR, some people call it ICLR. I noticed so many people there calling it ICLR, and it turns out someone was doing a poll on this, and turns out there is a good distribution of people. So people from the USA, China, and Canada tend to call it ICLR, and people from Russia and Europe mostly call it ICLR. I'm from none of these countries. I'm just going to keep calling it ICLR. ICLR has been growing in a number of submissions in the recent years, a lot. So I don't know if you can see this is ICLR 2025, and the number of submissions for this conference has risen to nearly 12,000 submissions, and the acceptance rate is like 32%, so that means that we have 4,000 nearly accepted papers, and covering that all is not going to be that easy. And usually you can't even see that many papers if you attend in person. So my best bet here is just to provide some trends or ideas about what is being presented and what is being worked on in the machine learning research field. And we're just going to stick to the idea level. We are not going to go very deep down into the papers. The hope is to just give you an idea of what are people working on. And ICLR is covering a broad range of topics nowadays. As you can see, LLMs are taking much of that. LLMs are the hot topic right now, so most of the submissions, like 20% of the submissions are in the LLM region. And you can see diffusions have a good submission number. And the thing that was interesting for me was that drug discovery and molecules are getting a lot of traction, as big as graphs or federated learning. Of course, there's some overlap that this graph is not covering, but I thought it's interesting to show which regions people are working more on. On today's agenda, we are first going to talk about ML in biology. As Philip said, my main focus in machine learning is ML in biology. And then we're going to see some other topics. There's a topic of hyperfitting, then the sparse autoencoders, and then unlearning and knowledge distillation. Hopefully, I'll give you a good idea of what people are working on, or more like the interesting topics. If we talk about biology a little bit, the main problems in biology that people are trying to work on are the design and prediction of the biological structures, and also their synthesizability. Today, we're going to focus on these two. But it's good to know that people are, in general, working on biological dynamics modeling and also multimodal biology data, like hospital data, patient data, text data. And also, there is efforts in interpretability and explainability of these models. So yeah, why do we care about the structure of biomolecular structures? Turns out that the structure of these objects are very important for their functionality and also their binding to each other. And this is very important. This brings us into drug discovery. In drug discovery, we have a model of the 3D dimensions of our objects, our biomolecules. We can have a better methods and we can have more accurate methods. And also this helps us understand the mechanics of these proteins or molecules and how they affect our body. As you can see, like some of the most common diseases like Alzheimer and Parkinson are due to misfolded proteins. So as you can see in the middle of the slide, we have a protein. This is this big blue blob. Wait. Yeah. This big blue shape is a protein, and this is a small molecule that is trying to bind to it. So the main objective in drug discovery, let's say in an abstract way, is to bind a small molecule to a protein in order to inhibit its function or remove it or do something with it. And most of the efforts in this field are towards this problem. Yeah, here you're seeing the same thing, but in a graph. And ligand means the small molecule, and the ligands usually bind to proteins. Proteins can also bind to protein. In the structure generation field, we have 3 kinds of problems. The first one is very famous because of AlphaFold. In protein folding, we are usually trying to get from the amino acid sequences to 3D atomic structures. Here you can see an example of an amino acid structure. It's just a sequence of amino acids, and this is the final structure. So when you put amino acids next to each other in our body, they fold into this structure, and it's really important for us to know the 3D coordinates of this structure. The second problem is the backbone generation. So in the backbone generation, we are not very much interested in the side chains. We are mainly interested in the main structure of the protein. So this is a coil, this is a sheet. We are mostly interested in this. We are not interested in this. So this makes the problem a little bit easier, but it's a different kind of problem. People are focusing on the desired shape rather than the given amino acid sequence. And the final one is generating of small molecules, 3D structures. So small molecules are usually represented using SMILE strings. This is a SMILE string. It's basically a syntactic way of writing the chemical formula of a small molecule. And then we are interested in getting the 3D positions and the graph structure of this. Moving on, here we start our papers. So the first paper that was really interesting to me is called Proteina, Scaling Flow-Based Protein Structure Generative Models. As I said earlier, in this problem, they are mostly interested about the structure of the protein, and they are going to condition their generation based on the shapes. It's based on a flow-based diffusion model, and they start from a noise, and they can condition it on fold classes to generate their desired structure. And the main point or the highlight of this work is the scalability and the extensiveness of the training data that they have adopted here. So if I just make it a little bit more clear, this is an amino acid. This is one amino acid, and every amino acid has an alpha carbon atom. And this is the side chain. This is like the part that we don't care about right now. And this is the alpha carbon. So when you put this together and they fold into a structure, they can fold into some known structures. Like this one is called a beta barrel structure, which has 150 residues. And the other one is called a Roseman fold. So I also don't know much about this. but apparently chemists and biologists do know about them, and they do care about the shape of these structures. So sometimes they just want a stable structure that looks like something. And in this work, they just show that when you start with smaller length sequences, like 400 residues, their model is competitive with other existing models, but their power is in like scaling the number of residues. And if you go up to 800, the other models collapse, and their model is working well. Yeah, we're just gonna hop between topics a little bit, but I think this is the point of the talk. So here, we are moving on a little bit. We are still talking about generating conformations for proteins, but here we are using language models instead of diffusion models, and this gives us a little bit of speed. And in this work, they are using a discrete VAE, discrete variational autoencoder, and they are learning a codebook. They are learning a codebook of structure tokens. So they have an encoder and a decoder, and they take the 3D structure of coordinates, and they learn this codebook of structure tokens. And then they take these structure tokens into their structure language models, and then they condition these language models on the amino acid sequence that we saw earlier. This is just a sequence. The sequence can be A, B, C. And they try to predict the structure tokens. And during inference, they are using this same language model to inference on amino acid sequences and generate some structure tokens. And then they use the decoder that they have trained earlier to decode this into a conformation, a 3D conformation of a molecule. This turns out to be faster than the other methods, as they show in their results section. And it's also more accurate in terms of RMSD. So RMSD is a metric for 3D structures. It is kind of like RMSE, but for 3D structures, it shows the similarness of two 3D structures to each other. And they show that their RMSD is comparable with MSA-based model and sequence-based models. And in this graph, they show that their speed is better than the previous methods. This is, in fact, basically due to the use of language models instead of diffusion models, which take many steps to generate their structure. Yeah, now we're gonna move a little bit more. We're gonna talk about the generation of small molecules. So far we were talking about proteins, now we are talking about small molecules. And one of the problems in drug discovery and the generation of small molecules is the bioisosteric drug design. In this case, we already have a molecule, but we need to add something to it. This can be due to many reasons. Sometimes we know a good molecule, but it's patented, we cannot use it. Sometimes it's not synthesizable, we need to change it a little bit. There are many reasons that we may want to change the molecule. And in this work, the researchers have used different representations of molecules. For example, the molecular structure, shape, and electrostatics and pharmacophores to learn a joint diffusion model on these representations. And during the inference, they can start with some part of the molecule that they already know, or the shape of it that they expect to be, and they can condition their diffusion model to generate the molecule that they want. So they can like control it and do this in-painting thing. So yeah, as I mentioned, synthesizability is a major topic and a major problem for molecules right now. And I noticed that some of research is going towards this direction, that people are tending more to this synthesizability. Why is it a problem? The problem is that when we generate molecules in silico, meaning through computer science algorithms, these algorithms have no idea of the physics and the chemistry underlying. And the problem is that we can usually generate invalid structures, or structures that are like not synthesizable, or structures that are ignoring the reactions. And sometimes they are usually actually very biased towards their training data. Most of our training data are like a small part of the accessible molecules. So our models tend to stick to them. Yeah, the first work that I'm going to present here is called Procedural Synthesis of Synthesizable Molecules. And here they break down the problem into a tree, and they try to like simulate it like the way we would generate code or programs. So here, every block or every edge is a piece of molecule. It's a fragment of a molecule. And these operators are chemical reactions. And they build up a tree for each molecule of like, how does this molecule come to be from its fragments through these reactions. And the way they train it is that for each molecule they build up this tree, and then we have this small little thing up here. It's the fingerprint. So what is a fingerprint? Fingerprint is just a binary sequence of code that encodes it encodes some characteristics of molecules. It can show us information about the molecule. So in this method, they use a GNN to mask parts of this tree, and then they train the tree based on the similarities of the fingerprints achieved through the predictions. Yeah, through the results, they show that they use the MPO benchmark, which is a benchmark for this kind of tasks. In MPO, we have different kind of proteins that we are trying to predict some small molecules for. And these are like examples of the proteins. And the binding affinity shows like how well we have done. And they show that in some of the select MPO tasks, they are better than the previous models, and they are generating synthesizable molecules. Another similar work in the synthesizability trend is SymflowNet. SymflowNet is kind of working on the same idea, but it's a little bit different. Here they have a diffusion model, and binding affinity is their reward. So they start from fragments or pieces of molecules that you can find from the enamine. Enamine is a molecule database and the point about enamine is that you can buy all of these molecules. And then they have a reaction database, and then they try to build up these molecules from the pieces that they can actually purchase, and they train their models based on the reward from the binding affinity. This plot is a little bit complicated, but the thing is that they use this graph transformer to get there. This is hard. Yeah, they use this graph transformer at each stage of their generation. And there's an MLP that suggests some reactions to build upon the small molecule that they've started with. And they can be like unimolecular template reactions, they can be bimolecular templates. And based on that, they generate their molecule. So at this point, we are gonna change our gears a little bit. We are gonna move out of the molecule world. We are done with the biology section. Here we are gonna attend to some other like core ML ideas. And I hope this part is gonna be more interesting for people. This idea came from DeepMind. And the researchers at DeepMind noticed that if they keep training their models that are already pre-trained and enter into this section of hyperfitting, they call it, it turns out that they get better generations. This is weird. Yeah, this is the plot that they share with us. They say that after lowering the loss, the training loss, just keep training, and the loss is just gonna go near zero. And for some data sets, this is gonna be better for the model. So before this, if you just do greedy sampling, if you have this context, and you ask the model to continue generate based on this context, it turns out normally trained llama is going to get like repetitive. Actually, this is done with greedy decoding, but later on in their paper, they show that even with sampling, this can get really repetitive. They show that if they keep hyperfitting their small llama model, it's actually going to make better generations. So they try to explain this in their paper a little bit, what is happening behind the scenes, but they also don't know very well what is happening. They put it actually for their future work to discover this. But for now, they're saying that if we use like human measuring preference, we ask the models to continue on that context, and we ask humans which continuation do they prefer. It turns out that hyperfitting the tiny llama model, the 1B model, can reach a performance of a bigger model, like an 8B model. It can go from 4.9 to 34.3. Yeah, and now we're going to attend the sparse autoencoders problem. So sparse autoencoders have recently gained some traction because of mechanistic interpretability, and Anthropic, I believe, has been pushing for this. This work is actually from OpenAI. Why are sparse autoencoders important? So the idea here is that we want to use these autoencoders to realize what is happening inside the activations of our neural network, let's say GPT. The problem is that we don't understand what is happening. It's really hard to decipher what is happening in the activations. For example, what we want to see is that if we put in two different documents, let's say one about politics, one about sports, we want to see different activations getting fired up to understand, okay, like this neuron is tending to politics, this neuron is tending to sports, but that doesn't happen. And it's really hard to decipher what is happening inside the black box. So here the idea is to learn an autoencoder, a sparse autoencoder, from the activations of specific layers, and to try to project each activation into new latents. And maybe then this will be more classified. We can like distinguish between the different neurons that are getting activated, and maybe then we can understand what is happening inside the big model. But it turns out that these ideas are working for GPT-2, and if we want to understand big models like GPT-4, we need to scale our autoencoders. And it turns out scaling out autoencoders aren't that easy. Like naively making them bigger isn't that easy. And yeah, in this work, Scaling and Evaluating Sparse Autoencoders, but Gao et al., they have been attending to this problem. The problem of scaling the autoencoders is that we tend to see dead latents. What are dead latents? Dead latents are the latents that stop activating, they stop firing up. So we have a bigger latent, but most of them are not firing up. And that's a problem, because it doesn't make any sense. Like, we made it bigger so we can use all of the latents. And the other problem is feature shrinking. Because we use the L1 penalty in the loss, we see that our features are getting smaller and smaller, and this becomes a problem in scaling them. So in this work, they suggest many solutions to mitigate these problems. Here I'm mentioning two of them. Like in one case, they use an auxiliary loss, take top k dead latents, and train them to predict the error of the reconstruction. And then they also use the top k activation functions. This turns out to be very effective in training their models, and this helps them to scale their autoencoders to bigger ones. So yeah, they can scale pretty impressively, and they scale up to 16 million latents, and they derive some scaling laws out of them, which are pretty smooth, and they are encouraging to look more into this field and see what's happening. I'm not sure if they have been sharing their findings out of the GPT-4, but if they do, that'll be an interesting future work. Yeah, the next topic is unlearning in machine learning. This one was actually new for me. I hadn't heard of unlearning, but it turns out it's so important that for the next ICML, there is a workshop dedicated to unlearning. So unlearning is the process of making the model forget some of the information that it has learned. Why would we need to do that? Obviously, the first reason is privacy. Maybe our model has learned something, some personal information that it's not supposed to, and we need the model to unlearn that. It can help us with security and robustness. It can help us correct biases. Maybe our model has learned something, some biases that we don't want it to generate anymore. So we can use unlearning to prevent retraining the model from scratch and fix it on the spot. And one of the interesting works in this section is using LoRa to fine-tune the model on documents that we know there are informations in that we don't want anymore. So let's assume there is a document from a certain company that has certain information about certain employees, and in this method we can only fine-tune on that document with omitting the data that we don't want the model to know. And with this fine-tuning, we can prevent the whole retraining of the model. So here, if you're familiar with LoRa, we freeze the pre-trained model, and we use some trick to add new weights to the model, which are not as big as the actual weights. And they introduced some tricks to make this work. There is this Fisher-weighted initialization, which is a specific initialization way for the LoRa weights, LoRa parameters. And they use this inverted hinge loss instead of the gradient ascent loss. So gradient ascent is the conventional loss for this topic, for this kind of methods. They're introducing this new inverted hinge loss to mitigate that. Yeah, most of the papers in this line of research are still pretty young, and the problem is that most of the evaluations are also young and they're not that sophisticated. This paper is discussing this idea. They are saying that most of the metrics to evaluate the unlearning methods are using only greedy decoding, and based on that, they are judging if the model has unlearned something or not. And their idea is that that's wrong. We shouldn't be doing that, and we should have some probabilistic method to accurately evaluate these models, because most of our generations are going to be probabilistic. We usually sample from our models. We don't do greedy decoding in the real world. Yeah, if you look at the density of the activations, if you take the greedy decoding will only make sure that there is no leakage here. But actually, we care about the whole spectra, and we need to make sure that a probabilistic sampling won't create any leakage. And their idea is that instead of doing a greedy decoding, we need to, of course, have many samples. We need to sample a lot from our model, and we need to come up with a probabilistic measure of information to evaluate our models. And now I'm gonna turn into knowledge distillation. Knowledge distillation, as most of you would know, is the art of getting a smaller model from our bigger model, or making the bigger model more efficient. And here I'm gonna mention two of the most more like not well known, or not they wouldn't be like considered knowledge distillation, but I think they're more interesting. Yeah, the first work is called Mini PLM, Knowledge Distillation for Pre-Training Language Models. In this work, they are using a teacher model to select the data. So they're not learning exactly from that teacher model, but they are using this teacher model to select their data and train a student model. So the thing is that they can run the teacher model ahead of time, and they can use the different sampling for many different students. So the thing is that they look at the probabilities generated by these models, and they do a comparison, and they can choose their strategy of learning based on this comparison. So they call it difference sampling. And in their experiments, they show that this is way more efficient and more effective than vanilla knowledge distillation methods. Yeah, the next work is considered weight sharing or pruning, model pruning. So the idea for this work is that most of the times when we have a new architecture, we need different sizes of this architecture. We need to train them separately, and that's compute expensive. And it's better to have a way to share the knowledge of the model. So the idea here is that we can just train the bigger model and train a router end-to-end in a way that a router learns for a smaller size of the model, which activations should I pick. So here you can ask the router, say I want, let's say I'm training a Llama 60B model, and I can ask the router that I want to export a smaller model, which is 50% of the parameters. And this router knows what proportion of the activations and the layers to take in order to make the smaller model work. And this router is being trained end to end. Yes, that was it. Any questions?
Does that work?
This works, I guess.
Okay. Thank you very much for the talk. Now, naturally, we have some time left over. If anyone has any questions, just put your hand up, and we'll. Oh. Does anyone else have the mics? Okay. It's me. I'm going to come to you.
Thank you for the presentation. So my question is, could you elaborate a little bit more about the hyperfitting? Because it's kind of counterintuitive and against everything we machine learning specialists have learned so far. What's the specification? Why does it work? Is it because the model is small, or there is any other specific thing for which this way works?
Yeah, sure. Thank you for your question. What did I do? Okay, I can't select anything. I can just go forward. Oh, maybe I can do. Anyway, for the hyperfitting problem, as I explained, they also don't know exactly what is happening. They just check what is not happening. They make sure, thank you, they make sure that the model is not cutting the tail of the probabilities, and they make sure that the model is not just repeating itself. But yeah, it's very counterintuitive, and they also don't know why it's happening. And they also only train small models. It's not certain that for bigger model this will work. And yeah, they have also tried it in vision models, vision language models. In those models, they also see a better performance for these specific small data sets. So they hyperfit only on small data sets. And they see that in those small data sets, the performance gets better.
A small follow-up question. If you go to the next slide, could you talk about the metrics? Yes. What does this context PPL and 25F pref mean?
This context PPL, I think, is based on this evaluation that they came up with. They just have a context, and they just ask the model to continue generating based on that, and they ask humans which one they prefer.
Okay, thank you.
Sure.
Does anyone? Oh, I see a question there.
Thank you for the presentation. My question is about the same topic. There was written that we should ignore the validation loss, and I wanted to ask if it's not important for the performance. When we are saying that the performance is better, what do we mean? Because if we go back to the figure, the validation loss is increasing, right?
Yeah, that's the thing. That's the weird thing that happens here. The validation loss is increasing, but it turns out humans prefer the generations of the hyperfitted models. That's the phenomenon here that needs explanation.
Okay, thank you. And also, when we say hyperfitting, could you please explain a little bit more what we mean?
That's just a term that they came up with, hyperfitting, which is like too much fitting.
Like more than overfitting?
Yeah, this is more than overfitting.
Okay, thank you.
Awesome. Any other questions? I'm looking. I'm not seeing anybody. So, oh, okay. Can we pass the mic to the gentleman on the side, on the flank? Thank you.
Yeah, thank you for the presentation. I want to ask about the model the biology model that was trained on graphs, you told, right? That, like the reactions between can you elaborate more on that, how this works? Like, what do they predict? How do they train it?
Yeah, sure. Thank you for your question. So in this work, as I said, they try to understand the reaction pathways of the molecules. So they just put it into a template. They create these templates of the generations of a molecule that can be generated through these fragments and through these reactions. And they use the fingerprints and the Tanimoto similarity metric to compare the newly generated molecules and make the model learn based on that. So later on, they can use this in different ways. They can have a piece of the molecule and like mask one part of it and ask the model to just generate that part.
Okay, thank you.
Sure.
Okay. Oh. Are there any other questions? Okay, if not, then let's give another round of applause for our speaker. Awesome. And we also do have refreshments here since we're finishing up. Please enjoy what's been furnished, and let's all have a bit of networking, chat a little bit more.